Today I'm going to talk about the central limit theorem and how it relates to the sampling distribution of the sample regression slope. These are important concepts that are used to interpret regression results. Keep this in mind. In real-world situations, we never actually know the value of population parameters, such as the population regression slope. As a result, we take a sample and use the sample statistics to estimate population parameters. Sampling distributions exist for all statistics. They're based on the concept of this question: what results would you get if you repeatedly took one sample after another using the same sample size for each sample from a population and calculated some statistic, such as the regression slope? It turns out that some pretty interesting and predictable things will happen. Because you're using different samples each time, the results will vary a little bit from one sample to the next. The sample slopes are called unbiased estimates of the true slope in the population. What does the term unbiased estimates mean? It means that some of the sample slopes will be a little bit too small, others will be a little too large. But if you average all the sample slopes, the average will equal the population slope. This is what it means to say the estimate is unbiased. I'm going to use a computer simulation to demonstrate this. The R code used for this simulation is saved in the class Blackboard folder named Regression Slope Simulation. You can open this file into R and run it and see what results you get. But here's a warning. The simulation takes 400,000 samples using several different sample sizes, so it does take a few minutes to run. In the simulation, I set the problem up with a known population regression equation. In the real world, of course, you don't know the population regression equation, but simulations let you ask a question like this: if this is the true relationship between X and Y in the population, what sample result would you expect to get if you took a sample from the population? In this problem, I used a population intercept of 2.0 and a population slope of 3.5. I added normally distributed random error with a mean of 0 and a standard deviation of 5. This means that I know the sample slope should be symmetrically distributed around 3.5. The standard error measures the standard deviation of the sampling distribution, and it should decline as the sample size increases. The computer simulation that I use starts by taking 100,000 different random samples using a sample size of 10 for each sample. It finds the slope of the sample regression equation for each of the 100,000 samples. Next, it does the same thing using a sample size of 25 for each sample. After that, it repeats the process using a sample size of 100 and finally a sample size of 300. And it plots a density graph for the 100,000 sample regression slopes. Here are the density plots. Each of the 4 plots is based on a sample of 100,000 different random samples. As the sample size increases from 10 to 25 to 100 and 300, you can clearly see that the distributions become less dispersed. Larger sample sizes give more precise estimates of the population parameter. These density plots give you a very accurate image of the sampling distributions. In this simulation, you learned that the standard deviation of a sampling distribution is called the standard error of the distribution. R includes the standard error in the regression computer output. The standard error is important because it's used to find confidence intervals, and it's also used to test hypotheses. By examining the density plots, you can verify that the sample slopes are unbiased estimates of the population slope. As the sample size increases, you can see that the regression coefficients converge near the new population slope of 3.5.